Right, okay, can you hear me? Right, okay, can you hear me? Alright, okay, well, we'll be getting started on data structures too, but first we have a quick recaps on prefix, static sums and max sums. So like this is, for static sums, you have a static unchanging array and Q queries where each query will ask you to find the sum of numbers from L to R. So like if you just brute force it for every query, for the worst case, you might have to like sum up all the numbers from the all the way from the front to the back. So that's O(n) for each query, and that's, if you have Q queries, that's O(q)n, which is very slow. But the big brain idea here is that you can use static sums to basically shorten the calculation for the sums. So let's say in this picture we have, if we want to have this, if you have to have this like brown part here, we can just take the blue part minus the red part, and then we have the brown, and then we have our answer. So we have our static sum array, and then if you want to calculate the sum from R to R, from L to R, you just take sum R minus sum L minus 1, which is, so like that's basically prefix sums. But note that this only works when your array is static and unchanging. If you can like try to think of why, but we will answer that later. So like for our algorithm, we still have Q queries, but we need to get and calculate the difference of two elements, which is only O1 and not On. So we have a OQ queries and the On pre-computation, which passes. Now it's onto max sum. Basically, yeah, given a static unchanging array, you can find L and R such that the sum of AL all the way to AR is maximized. Now you could just brute force all possible combinations of L and R, so that's n squared, and you still have to calculate the sum to find out which one has the maximum sum. That's On again, which is On cube, which is very, very bad. But so like, even if we use static sums to make calculating the sums faster, it's still On squared, which is very bad. So basically we have Candace's algorithm, which is basically at every step of the array you have two choices. You have a current sum. You basically have a current sum, and you have to make two choices, whether to add to this current sum or to start anew. It's like we have a new subarray, or we add this element to the subarray. So like in this right now, our first number is -2. So like if we add it to our array or we start anew, it's both -2. So we don't have a choice for the first one. But for the second one, if we add -3 to -2, it's -5. But if we start anew, you can see it's only -3, which is better. So therefore we choose -3 to be our current sum. So we go on, we can either add 4 to -3, or we can start anew from 4, which is better. So we choose 4 to fill up our current sum. Right? Does everyone understand this? Alright, okay guys, can you hear me? Alright, okay, so I think I'm just gonna like start on from the beginning for data structures 2. Basically, like before we have our static sums and our max sums if we know that. So we're just gonna quickly recap on that. So for static sums, we have a static, that's crazy, static array, and we have Q queries, and each query will ask us the sum from somewhere to somewhere. So like if we brute force the sums by just adding everything up for every possible query, then we have O(n) per query, because in the worst case you're gonna have to add up the entire array. So that's OQn complexity, which is not very optimal. But we can find that if we want to find a sum from somewhere to somewhere, we can just take the sum. So like we can just take this, let's say we want to find the sum of the brown part. In this case we can take the value of the blue part minus the value of the red part, and that gives us the answer. So that means, and this allows us to pre-compute all the cumulative sums, which is all the different red parts and the blue parts. So like we have our static sum array, which represents, it's like if you have a static sum array, and then the ith number in the array will represent the sum of numbers from A1 all the way to AI. So if we want to find out the sum from L to R, we can just take the sum, we can just take R in our sum array minus the sum of L minus 1. So because of that, we now have a O1 query, because we only need to find two numbers and take the difference of them. So it's now the total complexity is OQ with ON pre-computation, which is much faster, but we need to note that because it's called static sum, this only works when the array is unchanging. So you can try to think of why that might be the case. But first, we will recap max sum first. So given once again a static array, find L and R such that the sum of numbers from L to R is the maximum possible. So the brute force solution is to try every combination of L and R and then calculate the sum for each to see if it's the maximum. So that's ON cubed total, which is very, very bad. Now even if we use static sums to speed up the checking of the sums, you're still going to have ON, which is still quite sad. But we can use Candace's algorithm to store some values. So basically, I think I'll just skip to the visual demonstration part. We keep track of a best sum so far, we keep track of this, and then at every step we have two choices. We can either add this element to the current sum, or we just start a new one. So like in this case, our current sum is 0 and we are at -2. We can either add -2 to the sum, or we can start again from -2, which both gives us -2. So that's negative. So now our current sum becomes -2. If we go on to the next step, our current sum is -2, and if we add -3 to it, we get -5. But if we look at this, if we start a new array, if we start something, we start anew, we start at -3, which is actually better than -5. So therefore we put our -3 in, our current sum is now -3. And then if we move on, our next element is 4. So we can either have -3 plus 4, which is 1, or we start anew from 4. And in this case, like 4 is obviously better. So now our current sum becomes 4, and we just keep going on until we fill up the rest of the array, and then we find that our max sum is 13. which is basically this entire thing added together. Right, does anyone have questions about prefix sum and max sum? Okay, I assume that you have no questions. Alright, let's move on. So, but yes, as I said before, these things only work when the array is static. And this is because this is another way of calculating the max sum, but let's say we have a different problem now. We still have Q queries, but there can be two types of queries. A normal query that we've seen before, or we could change the value of a certain number. So now in this case, our prefix sum doesn't work anymore because now if we add something to a number, we need to change the entire static sum. So we need O n, and then so even though we can answer queries in O1 time, but if the query tells us to update a certain element, it's gonna take O(n) time, because we're gonna have, in the worst case, we have to update the entire static sum array. So if the first element changes, we're gonna have to add that value to every number after it, which is very slow. So now we're back to OQN, which is very bad. So how do we fix this? We can have segment trees. Yes, so basically segment trees, I know there's a thing about Fenwick trees, but segment trees are like technically easier to understand because they look more intuitively. So like, let's say we have an array with a bunch of values, and then we have a bunch of nodes in the trees, and then each node has basically a value and the range it covers. So the number at the top is the value, and the thing at the bottom is the range. So basically we build up our segment trees. So in this case, the question is asking us to find the sum. So in this case, the segment tree stores the sum. So this number at the top stores the sum of this range. So in this case, like, we have 3 and 8. So this node will be 11, this will be 13. And then basically we just build up our segment tree. So this is 24, and it represents the range from index 0 all the way to index 3. And this is our root node of the segment tree, which goes from 0 to 4, and the total sum is 24. Now basically, alright, this is some math, I don't care, but basically when we want to change the node, we have to let's say we want to change the value of index number 1, we're gonna have to go down from the tree. So we start at the root, which is a blue one, and then we go one step down these yellow nodes, and then we arrive at index 1, and then we change index 1. So like, I'm just gonna demonstrate. Let's say we want to change this from 8 to 6. So now we go all the way down from the root, and then we change this to 6. And then now we go back every step, and then we update the numbers. So now because this becomes 9, and then 9 plus 13 becomes 22, and then 22 plus 0 becomes 24. So now we have successfully updated our segment tree for this value. But like, you might say like, hey, that's still a lot of numbers to update. You know, it's much slower than just updating one element. But what this does is that it allows us to update in log n time, because the purpose of the segment tree is to balance out the queries and the updates. It's like, let's say in the prefix sum, we have for prefix sum, we have O1 queries, but we have ON updates. And then if we just like brute force the sum normally, we have O1 updates, but ON queries. So there's this imbalance between the querying and the updating. So, and it's going to cause you to TLE if like the question gives all queries or all updates. But what the segment tree does is allow us to have both log n updates and log n queries. So it evens out the time complexity and allows us to pass more complicated questions. So basically, if we want to query a tree, if we want to query a certain range, we basically have there's basically you have to basically calculate all the combinations. So like this, if you can either, if the range of the query can, the range, you have three options. Like the first one is the easiest one. The range of the query matches the range of the node exactly. So like in this case, you just return the value of the node, which is simple. But so the other case is that the range of the query fits exactly. So like, no, in this case it might not be exactly, but basically the entire query is either in the left or in the right. So it doesn't, there's that if it sits completely in the left or completely in the right, we just query down into that node and then repeat from there. But and then if the range sits like between the two halves, we cut the query into two, and then we query them separately, and then we add them together again. So like, let's say we want to query the sum from 1 all the way to 2. So like in this case, the left range has a node, the left side has a range of 0 to 3. So you can see that the query range of 1 to 2 fits completely in the left node. So that means we just recurse down to the left node here. But now in this case, you can see that the one on the left is from 0 to 1, and the one on the right is from 2 to 3. So in this case, the query has to be split. We have to split up the query and then query these two nodes separately. So now in these queries, so let's say we query the range from 1 to 1. So this node, the one with 11 on it, is going to see that 1 to 1 is completely to the right. So it passes the query to the right to this node with 8. So now this node with 8 sees that the range of the query matches exactly with the range of itself. So it just returns its value, which is 8. So this returns 8, and then the query for 2 returns 4. So now we are back to our node. We are back to our node with number 11 on it, and what it does is after it gets the answers for both queries, it just combines them together. In this case, because they're asking for addition, so they just adds them together, and then you have 12, and then it just goes, and then it sends the answer back to the node with 24, and it sends it back up to the root, and then you get the answer of 12. Sorry, 12. So now it sends the answer of 12 all the way back, and then you get your answer of 12. So that's how it does. Now like I've looked at these slides, and then this is a bit complicated because like there's a lot of templates and there's a lot of template writing and stuff. So I'm actually just gonna show you my own code. Okay, so just wait a moment while I get my own code. Right, okay, can you guys see my code? Yeah, I think you can. So basically, for segment trees, we need to use a thing called a struct, which is basically like a custom data structure. And then so first we have our SEM, which is your S and E is basically your range of the segment tree. And then your M is the middle point, because remember, if your node is at the top of if there are nodes below you have to like split it into two. So your M, this variable M is used for splitting it into two. And then your value will be basically the sum. And then you basically create new nodes. So basically, like, because we're creating a structure, a custom data structure called a node, so we can actually, and this allows us to actually like put nodes inside a node. So basically we are creating this, which is now, like, this is a bit complicated, but basically, like, what you need to know is that basically L and R point to other nodes. Basically they are pointers, and they point to another node where which is the nodes at the left and right of your node. So basically this is what we use to create the node. So we have a S and E, which is the range. So we just set the range and then the midpoint. And then because we haven't set any values yet, so like initially all the values we can just set it as 0. So you can see here we are checking if it's basically, this checks if the node can be split into two. We split them into two, and then we fill up the left and right. We basically fill up the left and right, and then we create new nodes again, which we use our M value to do that. Now for updates, we are trying to change the value of number X to the value of V. So point update. So basically we want to go all the way down. So let's say if S equals E. So if we go back to the slides, if you check the slides, basically this S equals to E only occurs when it's basically your node is only storing the value of one number. So basically it's at the very bottom of the tree. So once we reach the bottom, we can just update the value. And then, but if it's not at the bottom, we check whether it's in the left side or the right side. So like if this case X is less than M, so basically the midpoint is somewhere, and then the value of X is less than it, then we know that it's to the left side of it. So we update the left child, and the same goes for the right child. And then after we update, and then if it's in the right child, we just update the right child. And then after we update this, we need to change it so that we need to update yourself, so that you actually you need to update yourself so that the range sum is now accurate. Just like the minimum is because I changed it for some other question, but yeah, I'm just gonna change it back. So wait, is everyone clear with creating nodes and updating nodes before I go on to queries? Like, if you have any questions, like, ask them now, because it's like it is quite confusing the first time you learn it. Right, if there are no questions, right, if you have any questions, you can ask in the live chat or just ask in the Discord. Alright, if there are no questions, we'll be moving on now. Alright, now on to queries. So basically our queries, we query all the way from the start to the end. So like, again, if in the first case, as we seen in the slides, if the range of the query fits exactly with the range of the node, we can just return the value of the node. But in this case, but if the so like why we're for case 2, in this case, so basically the rightmost end of the query is less than the midpoint. That means the query fits entirely in the left side, the left child of the current node. So in this case, we'll just recursively query down to the left node. And then the same thing goes if the leftmost end of the query is like more than the midpoint. It means that this query is sitting completely inside the right hand side. So in this case, we'll just query to the right. And then now for the final case where the query is split between the two nodes, we'll just query them separately and add them together. So we'll query from the left all the way to the midpoint, and then we query from the right all the way to the midpoint. So and then we add them together. So this is basically how a segment tree works. And I hope that this is a bit more clearer because the code is all annotated. And then basically remember that it's like you have to put the weird arrow thingy, and it's not like node.update because pointers don't work that way. Because it's a pointer, you have to basically like root points to update. So that means you like update this. So basically at the very end, we'll create a pointer to a node called root, and basically that's the very top of our segment tree. So basically we at the start of the question, we just create a new node at the root, and then it will, because it creates in the constructor function, it creates new nodes by itself if it's not at the bottom. So when we run this, we just create the entire subtree, the seg tree. And then basically that's it. We can update or we can query. So yeah, so if we guys, go solve. Now we have to go solve segment tree on Codebreaker. Just know that for segment 3, like the question on Codebreaker, it's asking for the minimum value It's asking for the minimum value. So when you combine them, instead of adding them, you take the minimum value. Can I give you until about 2:30 to try out this question? Because it can be quite confusing if you're doing it for the first time. So you have if you have any questions, just like open like unmute yourself in the chat, or ask or ask one of the trainers. Hey guys, I'll be ending the stream and letting Brian take over right now. So yeah, but if you have any questions, you can still ask them, and just like ask in the advanced voice chat, or in the or like yeah, just ask in the advanced voice chat, or ask in the questions like under advanced stuff in the forum.